are capital N molecules. Now we use little n in PV equals nRT, standing for the number of moles. Big N stands for the number of molecules. And we're going to assume that all these molecules are moving in the same direction. We're still not going to go into the three-dimensional case. And that direction is implicitly the same as the direction as in the previous example. So we have a delta T. Okay. Now we're going to let delta T be the time between collisions, not the round trip time of one molecule, although we could do that, as we'll see in a minute. So we have several choices. We could let delta T be the time between collisions, which would be 1 over n times as great on the average as if we had just one molecule. If we had 10 molecules, they're going to hit in 1/10. We're going to have collisions that are 10 times closer together in time. So they'll be 1/10 as far apart. So delta T between collisions will be 1 over n times as great. Or we could say delta P in the time delta T over 2, delta T equals 2L over V is n times as great. That is, in the time it takes any one molecule to make the round trip, we're going to have n times as many collisions. So using the same delta T as we did before, delta P becomes n times as great. Okay, in this case we'd have the same delta P as we did before. In this case, we have the same delta T as we did before. If we have the same delta P, that means our delta T will be 1 over n times as great. If we have the same delta T, then our delta P will be n times as great. Either way, or using common sense, we see that the average pressure will be n times as great as it was before. Since we have n molecules all doing the same thing that the one molecule did before, they're going to have n times the effect. So now we see that the average pressure will be n times a constant times T over V. So we could say PV equals big N times a constant times T, and this constant will be something that's related to R, although it won't be the same because remember here N is being measured in number of molecules, not moles. Our third model, we let the kinetic energy go into all directions within the cylinder. And we're going to assume for right now that we have monatomic gas, an ideal monatomic gas. So that as we can see with the billiard ball simulation, the kinetic energy equipartitions itself. Remember, in that simulation, all the molecules are moving in the horizontal direction at the beginning, and then they start colliding, and very quickly they get y velocities, and the kinetic energy partitions itself equally within just a couple seconds in that simulation, to where you can't tell that there was ever all the kinetic energy was ever in the x direction. Okay? And if there's a z direction, we equipartition into the z direction also. This means that the kinetic energy, average kinetic energy, goes over all three directions. Now, if the x direction is along the axis of the cylinder, along the cylinder axis, then it's only the average kinetic energy in the x direction, only the velocity in the x direction, that affects the change of momentum when we hit the end of the cylinder. If we're moving in this direction and hit the end of the cylinder, bounce off this way, it's only this component, the x component of this velocity, that changes. The y and z components are going to stay the same, and only the x kinetic energy, only the x velocity, and therefore the x kinetic energy has an effect on the force at that end. So only the x force affects the average pressure, and also we can say that the average x kinetic energy is 1/3 of the average kinetic energy of a molecule. Now notice we're talking about the average kinetic energy of a molecule and not the kinetic energy, because as you see from the billiard ball simulation, these molecules are going to change velocity as they collide. Some are going to pick up velocity, some are going to lose velocity. They're not all going to stay at the same velocity. They're not all, therefore, going to have the same kinetic energy. For that reason, we talk about the average kinetic energy here, and that's the reason that we talk about the root mean square speed, the square root of the average of the squared speeds of the molecules. The squared speeds are what give us the kinetic energy. And if we want to average velocity that has a meaning for kinetic energy, we have to use that root mean square. And if you think about that, that's not too hard to understand. In this case, then, we're going to get pressure equals n number of molecules. Constant isn't there. I wrote it down out of habit and had to cross it out. But then that's going to be, remember it was 2 times the kinetic energy before. Now it's 2 times just the x kinetic energy. The x kinetic energy being 1/3 the average kinetic energy. So it's 2 times the average x kinetic energy divided by velocity or volume. The pressure is therefore given by this expression, which we're going to write as 2/3 times the average kinetic energy. If the average kinetic energy is proportional to the temperature, then we replace average kinetic energy with some constant times temperature. And we get, ultimately, PV equals 2/3 times big N times that constant times T. Bring the 2/3 out in front, that's exactly what this would look like. Now this is looking a whole lot like the PV equals nRT, except we have capital N, and instead of an R we have a constant in that 2/3. Okay? Well, 2/3 of the constant is what we're going to call K. We're just going to lump 2/3 times a constant in here and call it K, and that's what we're going to call Boltzmann's constant. It looks like Botman here. Started to cross my L and didn't pick that up. I apologize for that. Anyhow, K is Boltzmann's constant. And it turns out that K has this value. We get that value actually by first getting R and then dividing by Avogadro's number. So we'll see in a minute where that comes from. But this is the constant that we use. And then we have PV equals capital N times 2/3 of constant is K times T. And that looks like this. Now we're going to use Avogadro's number in the next clip to relate this to the R, the gas constant, and see where all this, how all this ties up and how we can use some of it.